Okay, you can see my screen?
Yes.
Anybody?
Yes.
Yes. Okay.
Yes.
All right. So the topic of tonight is a bit about eyepieces. And I'm breaking it into 4 sections. So I'm going to talk about eyepieces specifically, then accessories that are related to eyepieces. And then, because it's very important to understand why we have an eyepiece and what they must do, I'm going to discuss the serious topic of vision and the human eye, which to me is the most important part of the presentation. And then a little bit about choosing eyepieces afterwards. Right, so the first question is, do you need an eyepiece at all? And surprisingly, the answer is a qualified no. You can put your eye to the telescope and you can actually see something without an eyepiece. But it's really not a satisfactory experience visually. You'll have a very small field of view and you will strain to keep it in focus. Some telescopes are never used visually, and so obviously they don't need an eyepiece. And the largest telescope I'm aware of that is available for public viewing is this one, 2.7 meter telescope in Texas. And because different people have different needs, right, you might have different choices to be made, right? So as we delve into the topic, I'll repeat some of the concepts that need to be internalized. And hopefully you'll come out with a rounded view and be in a position to make suitable decisions on the subject. So what does the eyepiece do? The eyepiece matches the eye to the telescope, and that is quite important. So we'll look into the eye later, as I mentioned, right? Simple designs do not really work very well, and especially on fast telescopes with short focal ratios. The slow, longer focal length telescopes are more tolerant, and eyepieces are made for specific purposes. So you get integrated systems like binoculars and spotting scopes and rifle scopes that are a system in its entirety, and then the optical design can be traded off between various parts of the system. And so those eyepieces may or may not work well on an ordinary telescope if you extract them. Generally they do, but they might not always, right? But they don't have to fit in a standard telescope focuser, so they can be adapted to their purpose. And if you extract it, you can make it fit, right? And there have been some things that have driven rapid evolution in eyepiece design in recent years. The advent of CAD/CAM systems, industrial automation, ray tracing software, material science, and notably a growing market that demands better, and especially because of the advent of large, fast, small focal ratio amateur telescopes. So the basic point is that it's got to match the telescope to your eye, and there's a variety to choose from, and they're designed to work at a particular F ratio, but they can work to a slightly less degree of quality outside of those parameters. And mostly you will find them that will fit standard focuses, just not always, right? And the evolution has been dramatic in recent years, and it is continuing. So the eyepiece literally is half of the telescope. And it is therefore quite important. So the sort of train of the light is from the source object, right, which is very large compared to us on Earth. It traverses the immensity of space only to pass through our turbulent atmosphere, which will destroy some detail. And then the light is collected by the telescope's objective, be it a lens or a mirror, and that is then focused onto a point where there's a small image of this very large object now hovering right near the exit of your telescope, right? And to be able to focus our eye closely on the small object is why we have to have something like a magnifying glass that takes this diverging series of rays and makes them parallel so that the eye can actually handle it, right? And for higher magnifications, really, we're looking at a microscope in effect, right? Part of the field of view will be obstructed by mechanical components or the ability of the objective to give a suitable field of view. And so vignetting will occur. Finally, of course, it gets your eye, and then the eye has a lens that will take this parallel beam of light and refocus it onto the retina, and you'll finally be able to see, right? So the scale of the image depends on the object size, right, its distance, and the telescope's focal length. The quality of the image delivered by the primary and is largely affected by the atmosphere and by the quality of the optics of the objective. The actual image size can be constrained mechanically, and your field of view is constrained equally by that. Eyepieces often do have a field stop at the focal plane, so at this point, deliberately to give you a nice sharp edge to your image. You may or may not like that, but what it's really doing is blocking out the poorer parts of the image and defining the visible field to give you a satisfactory view. And yes, you can pile on the magnification, but eventually you'll run out of detail. So you can imagine if you see a television set in the distance, it just looks like a blur. You get closer and closer. That's like you are enlarging the image. You can see it getting bigger and bigger, and finally it all looks very nice and clear. But if you get too close to it, then the image breaks down because it just doesn't have enough detail at that level. So, you know, in a TV, it's pixelated. Here, it just gets fuzzy, right? And every step of the way is a potential place for the final image to be degraded, right? So that means that your eyepiece is equally as important as your objective. If you don't have a quality eyepiece, you can't extract the full amount of information provided by your objective. Now, making a good quality eyepiece can be more complex and more difficult than making the objective. And that's why it's quite expensive, even though it is a small physical part of the telescope. So the designs have been progressing. And in the early days of the telescope, you just have a single little lens, like Galileo had, a little biconcave lens as the eyepiece. Not very satisfactory at all. So I'm going to tell you a little bit about the evolution of the designs. And these cross sections are drawn with the field lens towards the telescope on the right. So this is the field lens here that's accepting the light from the telescope, and then it exits towards the eye from what's called the eye lens. So the red arrows show you the path of light in these various designs. Now, when people like myself were younger, then the two-element Huygens and Ranston designs were most prevalent. You still get them today in cheap telescopes. They have done their job, but we can do better. So the advent of World War II brought into being a need for high-quality, wide-field eyepieces for gun sights. And you know, in a life and death situation, you have a higher demand, and cost is of a lesser issue than in the normal sort of commercial environment. And so the Erfler design was briefly mass-produced around the Second World War, and the post-war military surplus market, where these things ended up on, gave amateurs a taste for these wide fields of view and reasonably well-defined images. And so we started demanding more, right? So in about the 1980s or so, orthoscopics became the norm, and earthless were quite readily available, new ones, not just surplus ones. Now, in the 60s, it wasn't believed that orthoscopic would ever become financially cheap enough to be a commercial proposition and become mainstream. But since then, newer designs have actually entered. So the Plossl, which is fewer elements than orthoscopic, but with quite exquisite detail, right, started to become the mainstream for like planetary observers who needed to see the fine detail. And then later Super Plossl was developed, which is really a sort of Ramsden lens or a Plossl, but where you have a symmetrical design. So it doesn't matter which way through the light goes, it sees the same path, because this pair of lenses and that pair of lenses are the same, right? So what the design has done is it's used more materials than in a Plossl, but because these lenses are of the same type, you have an economy of scale. There are fewer. Each of the Plossl lenses is distinctly different and has to be manufactured separately to be put together as a set. Whereas with a Super Plossl, you've got pairs here that are the same. So mass production techniques using the common elements have entailed cost savings, and this allows a bigger market to be addressed. So this is pretty much what you should expect on any reasonable telescope. When you buy it, it should at least have one eyepiece, and it should be something like a Super Plossl, whereas previously you would have a Huygens or a Ramsden. Now, already in the 1960s, the US space race drove the need for superior quality, very wide field eyepieces in specialist fields. And a guy by the name of Al Nagler invented a new kind of eyepiece for the Lunar Excursion Module trainer, where the astronauts basically got the experience that they were looking through a porthole and seeing the lunar surface, when what was out there was actually a small model with a sort of giant microscope attached to it, with a very big eyepiece. And later, he started a company and started making telescope eyepieces. And this was the first Nagler to be available in 1981. And since then, advances in material science have brought new exotic glasses to an affordable level, and computer-aided design kicked in. And that, together with computer automated manufacturing processes, has brought a whole slew of new novel designs to the market that previously wouldn't have been possible. So many of these are actually a wide field eyepiece, if you look at these components here, right? But built in ahead of them is a Barlow-like element, or a complex Smith lens, SMYTH. So what you have here is the advantages of a low-power eyepiece with a nice eye relief and wide field of view that's now being amplified by the Barlow elements that are built in, right? And the whole design is optimized. Now, naturally, these exotic designs are far more complex to manufacture, and they attract premium prices. So the optical design is, let's say, the primary aspect that you'll look at when choosing an eyepiece, because that determines how the eyepiece performs. And some are better suited for short focal length telescopes, which place a much higher demand on the eyepiece performance. The simpler designs are fine on very long focal length instruments. So we can move on to the mechanical aspects now. And if we look at this, then the first thing you'll notice is the barrel size. So that's the part that actually connects into the focus of your telescope, right? And at a relatively early stage in the 1900s, there was a need for mechanical standardization. to enable interchangeability of the eyepieces. And once that was recognized, you started to find families of eyepieces of different sizes. So although it started in Germany, the Japanese popularized the 0.965-inch eyepiece, which you still find today, right? That's a 24.5 millimeter diameter barrel. Nobody seems to know why this was chosen. But in its heyday, companies like Zeiss, Nikon, Unitron, and Nihon Seiko made exquisite examples of these tiny eyepieces, but really beautiful, beautiful optics. But this size has mostly been abandoned due to the adoption of larger focuses, and is now only used for entry-level instruments due to the cost constraints. And the recent versions manufactured in the last 25 years or so tend to be very poor quality. So buying those today is a false economy. The French, because they have to be different, reversely chose the Paris inch, which is 27.07 millimeters or 1.066 inches. Nobody knows why, and thankfully that is long since defunct. So if you find one of those, it will be a big surprise to you. The British, on the other hand, decided on the RAS, it's for the Royal Astronomical Society, RAS thread. So this ultimately was a standard plumbing fitting, 1¼ inches in diameter, and with a 16 teeth per inch thread on it. So this is secure because it screws in, you don't have to clamp it in place. But of course, it's difficult to exchange without losing your target, because it takes time to unscrew and maybe you wobble the telescope in the process, right? The Americans are quite pragmatic. And so they went to the 1¼ inch barrel diameter. That's quite ubiquitous these days. And since then, we've moved on to the 2-inch standard, which is now becoming the norm. An emerging standard is the 3-inch barrel. That's quite an expensive proposition, suitable really for much larger telescopes than what you and I are likely to have. Now, the question is why this progression, when for so long 0.965 inch was okay, and eventually 1¼ came along and was there for a long enough time. Now suddenly we are moving to 2-inch, and it's become the norm in just a very few years. And the answer to that is that the larger the barrel size, the larger the field stop inside, and therefore the available field of view. So small barrels provide a limiting factor to the possible field of view. So for a 0.965 millimeter eyepiece, the maximum apparent field of view is only 40 degrees, right? So now note the tiny, tiny little eye lenses in these things. I mean, they, especially in the shorter focal lengths, they are really, really small. And it's hard, believe it or not, to make a small lens accurately, even though it's not a lot of material involved. Now, larger barrels allow more glass. There's more physical size that you can put in there. And so that can accommodate these exotic new designs to produce modern benefits. So long eye relief, that is the height above the eyepiece at which you must place your eye to see the full field of view. And that normally scales with the focal length. So if you've got a 3 millimeter eyepiece, you'll have a very small eye relief, whereas with a 30 millimeter, you'll have like 10 times as much typically, right? But the larger sizes are nonetheless mechanically limited, because you've got to put your face there and your nose will collide with it. So if you've got a 3-inch eyepiece, the distance between your nose and the center of one eye is more than the 1½ inches of a 3-inch. So you will see this conical arrangement called the volcano top in many of these larger eyepieces. And that's really so that you can get your eye there without your nose colliding. So optimizing these designs takes a lot of practical aspects into consideration. Now, some pieces are multi-standard, so you'll see that might have a skirt here that's 2-inch, and then a barrel that's 1¼ inch. Like this is a Barter Planetarium, or this one on the right here, which is a TeleView Nagler. And some will have a separate piece that can screw on, like this TeleView Ethos. So you've got a 1 1/4 inch, but you can put a 2-inch barrel on there, so you can fit it onto whichever focuser you want, right? So you need a dedicated adapter sometime. Now, some eyepieces have hidden virtues, right? Things that are not apparent by just looking at the eyepiece. And so you've got the common things that you would normally notice when you look at an eyepiece. You might have an eye cup that can fold down or pop up so that you can shield your eye from extraneous light, or put it down so that you can use it with your glasses, right? Rubber grips so that you're less likely to drop it when your fingers are frozen, right? They might contain an inert gas and be sealed, and that means that it's gas tight and waterproof, and so you're not going to have internal fogging if you have a big change in temperature. Some sets in a range are parfocal, and parfocal means you can interchange your eyepieces from that set without having to refocus your telescope, maybe touch it up slightly, but essentially you don't have to make much of a change to your focus in order to swap from one eyepiece to another. That's quite a convenience, right? Generally, they will have on the nose threads that will allow you to screw filters on. And you will see here security grooves on this Barder thing here, or like on this William Optics, how it has a sort of conical shape that tapers inwards. So when you clamp it, it will hold tight in the focuser with no chance of it slipping out and falling to the ground, right? A few of them have got hidden features, like the Barder Hyperion here, where if you take the rubber cups off, you will see underneath that there are screw threads, and they've got a whole system of adapters that allow you to couple this to your camera so that you can, for instance, do projection, eyepiece projection for planetary imaging, where you need extreme magnifications to get any reasonable size image on your sensor. The next question is that of mass. This is quite obvious. It scales rapidly with the barrel size, and you have to ask yourself, will you be able to balance your telescope? This is a very real thing. So if you look at the range of masses, a 0.965 inch barrel size, typically the eyepieces only weigh 30 to 45 grams. But if you go to a modern 2-inch, it can be as much as 1.5 kilograms. So if you put a 1.5 kilogram eyepiece on a telescope that was only expecting 30 to 100 grams, the whole thing is likely to nosedive. So you'll have to then balance your telescope. Now, we jokingly refer to these big things as grenades, but I took a look, and grenades, in fact, are quite possibly compared to the eyepiece. Here you've got the Mills bomb from World War II, the grenade that most people are most familiar with, and these are the sizes. The Mills bomb is smaller. It's only 64 millimeters rather than 85 millimeters in diameter, and it only weighs like 3/4 kilogram instead of more than 1 kilogram for this. And this is not the heaviest eyepiece I've encountered. It just happens to be the heaviest one in my particular collection. So you need to take the mass into consideration. You might have to put some sort of balancing mechanism on your telescope so that if you swap between eyepieces, you can retain your balance. Then, of course, we have optical characteristics, of which the focal length is the one that we are going to see as being the most obvious, because we will swap out our eyepieces. They're all characterized by their focal length. And so although they are available, you will seldom get an eyepiece less than 3.5 millimeters in focal length. They're usually around about 4 or 5 millimeters, like these green ones. Here's a 3.5 millimeter, there's a 5 millimeter here, right? And equally, you seldom get anything more than a 40 millimeter. So this one here is 40 millimeters. in focal length, right? That said, I do have an old 70mm Kellner, and I've built a 100mm focal length Plossel for use on a very large telescope, on the 60-inch in Bloemfontein, in fact. But that's got such an extreme focal length, it's hard to get a low power without being extreme with your eyepieces. Then you'll find that if you get a set of eyepieces from a family, they might have common characteristics, like they could be parfocal, for example, like these ones in red. So these are families where there's a lot of matching between the eyepieces to make it easier in use. You can get zoom eyepieces, and so the advantage of that is you can have one eyepiece with several effective focal lengths, right? But is this good or bad? Well, it depends. Having a decent zoom on your telescope is useful for travel because you don't have to carry so many separate items with you. And if you've got something like a library telescope, which is lent out or hired out, then you can bolt one of these in so it becomes an integral part of the telescope. So there's fewer items to worry about. It's also good for bino viewers where you need two eyepieces, and it gets very expensive very rapidly if you have to buy matching pairs all the time. But I have to tell you that when it comes to zooms, the quality can be extremely variable. Planetarium, go for it. It'll be fine, all right? But this kind here, which you used to see and which gave them a generically bad name, no good, all right? So most common ones are not worth looking at, but if you buy a high quality one, it's okay. It's generally better to get a few decent fixed focal length eyepieces. So the effects of the focal length are that you get varying magnification, because if you divide the focal length of your objective, your mirror or the front lens of your telescope by the focal length of your eyepiece, then you will get a different magnification. So the longer the focal length of your eyepiece, then the lower the magnification. So if you have the same apparent field of view in your eyepieces, so delimited by this black circle, you can see, say, looking at the moon at 10 times, it'll look at this, and then higher magnification, but with the same apparent field of view eyepiece design, go to 15 times, now it's filling the view, and then it overflows the view. These are just illustrative images here, and the numbers don't really mean that much, just to show you that as your magnification increases, what's happening is you're actually looking at a smaller part of the image provided by the telescope, because that doesn't change. It just produces an image, and then you analyze that image by changing your eyepieces. So you go to shorter and shorter focal lengths, you will have higher and higher magnifications, but you're looking just at the same central portion now. You lose the whole field of view. And because you're taking a small part and you're stretching it to a wider apparent field of view, then you will see that the image gets fainter and fainter as you pile on the magnification, right? So the telescope only delivers a certain amount of detail. And that means that magnification has its limits, because in the end, you're going to run out of resolution if you pile on the magnification. And you also have to consider the effects of the atmosphere. So on the low end, low magnification, then the exit pupil of the telescope might be too large for your eye's pupil to accommodate. And in Newtonians or Schmidt-Cassegrains, which have a central obstruction, then the shadow of the secondary is a hole in the middle of the image. And so if you have a very, very wide view at low power, you will have an objectionable hole in the middle. And at the high end, you eventually run out of resolution, and it just becomes a murky mass without any interesting detail in it. And of course, that's partly limited by the atmosphere, and any vibration of the telescope will be highlighted, so it's very sensitive to that. And both extremes, whether it's very low or very high power magnifications, are affected by defects in your eye, and we will discuss the interaction with the eye a bit later. So looking at extremes, I've had the pleasure of using the 60-inch Rockefeller telescope at Boyden Observatory, and hopefully some of you will go and have that pleasure too in a couple of weeks' time. This started as a Newtonian, as you can see in this inset here. The guy's on a little sort of cage that's getting him to where the eyepiece would be. But later the optics were changed, and now it's a Cassegrain with a much, much longer focal length. That's a 1.5 meter diameter primary, and it now has a 32.82 meter focal length. That's the third largest telescope in South Africa after SALT and the 74-inch at Sutherland, which was previously in Pretoria. And it's the fourth largest on the continent of Africa because there's another 74-inch in Cairo. Now for this, I made a 100 millimeter focal length wide field eyepiece that yielded a medium power of 273 times, right? With a 2.4 millimeter diameter exit pupil, and that was really nice for visual observing. So Amiga Centauri covered several eyepiece fields, and it took 20 minutes just to get Jupiter into the field of view, because the field of view is, the true field of view is so narrow. So if you wanted a low power eyepiece for this instrument with such a long focal length, you would need a 250 millimeter eyepiece, right? I did a similar thing for the 26-inch refractor in Joburg, and then both of those eyepieces mysteriously vanished. But recently I replaced the Joburg one with a better one. Instead of being a Plossel, it's more exotic design with 8 elements. And that's got a more moderate focal length. But on the other extreme, you get eyepieces below 2 millimeters focal length. They tend to be very uncomfortable to use. So the next characteristic of your eyepiece is the apparent field of view. So the telescope will provide an image, and you can look at this image, and you will have a true field of view. That's what part of the sky can you see, but you can enlarge that field as far as your eye discerns it to give you a higher apparent field of view. So I've got here an image of the moon, and superimposed on it are these rings going to larger and larger and larger apparent fields of view, but it's the same image produced by the telescope, but if you put different eyepieces on, you will be able to see different amounts of that true field of view. So in the middle is a 35 millimeter 50-degree eyepiece that I made, right? Then we go to 72 millimeters, the blue one over here, and then the yellow ring is 82, sorry, not millimeters, degrees, 82 degrees, then out to 100 degrees, and finally 110 degrees. So these very wide field eyepieces are nice, but you have to ask yourself whether your telescope is going to give good quality image at such a large area. Usually the image is good in the center and it degrades towards the edge. So you have to determine whether it's right for your telescope. Why do we like these? It used to be that 50 degrees was a premium eyepiece, right? And this is an 8-element eyepiece. It performs well, and it's actually very comfortable to use, right? But wider fields are nice. People like it. You have to roll your eye around to see the periphery, because your actual field of view is much less than 110 degrees, your field of sharp vision. The periphery vision is really just to detect movement more than anything else. But for short focal length eyepieces, excuse me, which produce high magnification, then having a wide field of view, apparent field of view of your eyepiece helps to find the object and to keep it in the field of view. And this is especially useful if your tracking is poor. So with the advent of large Dobsonian telescopes that don't track, having a wide field eyepiece allows you to keep the image in the field of view for longer, and that is very useful. So eye relief is the separation between your eye lens of the eyepiece and your eye's cornea, basically, right? And you want this to be a reasonable amount for comfort, so that you're not pressing your eye up against the eyepiece, you're not brushing your eyelashes up against the eyepiece. And it allows you to wear your glasses if necessary, and not to be overlooked. It helps to keep the eye lens clean. I'm telling you, beware the mascara. So if you have a public viewing, you're going to have people coming along, and you're going to end up with a grubby eyepiece if it's a short eye relief, because you've got to put your eye so close. So the eye relief generally scales with the focal length. So short focal length, you will get a small eye relief. Clever optical design can help, but of course at a cost. And longer eye relief is more comfortable, but you might need to put an eye cup in here. That's why some eyepieces have these flexible rubber eye cups that can pop up in order to shield the extraneous ambient light, and also to help you keep your eye centered on the eyepiece, right? So long eye relief and eye cups are strongly recommended for public viewing. And as I said, especially keep your precious eyepieces free of mascara. Now, a short eye relief can present a significant danger to the observer. Now, that's not least because you might actually scrape your cornea on the mechanics, right? And rifle scopes, as this example is, the rifle has recoil, so this thing tends to jump backwards. And if you don't have a long eye relief there, you're going to jam this telescope straight into your eye. That can be very serious with a recoil. As a little anecdote, I read of an elderly observer who was alone atop a remote mountain observing in cold weather. And he turned away from the eyepiece to make some notes and found that his vision was suddenly blurry. And it turned out that his contact lens had frozen onto the eyepiece. And when he turned his head away, then the contact lens stayed on the eyepiece, and that explained the blurry vision. Now, just imagine if that had been his cornea frozen to the eyepiece, and nobody around to help him, and the telescope is moving on its tracking system, and what do? Imagine if the eyepiece had been an RAS thread where you couldn't just unclamp it and pull it out and separate yourself from the telescope. What do? You know, that could have been very, very tragic. All right, so the eyepiece has optical and mechanical elements, and there are ways of optimizing these to help improve the performance. So a good quality eyepiece will use exotic glass types to control the aberrations, and measures will be taken to control glare, right? So that is light that's coming in that's not properly focused. So good anti-reflection coatings are one attribute that a premium eyepiece will have. And if you look at these eyepieces here, I use some extreme lighting to show off these internal reflections, right? Every single glass surface has the potential for reflection. So that means for every element in here, there are two surfaces that can reflect. And if you've got an 8-element eyepiece, that's 16 surfaces. So the internal reflections occur when there's an abrupt change in the refractive index. So that's then at the air-glass interfaces. Sometimes you will find the lenses are in contact with one another, and so that sort of reduces the air-glass interfaces. Now, single internal reflections can scatter the light across the field, and even numbers of reflections can lead to ghosts. So what you're seeing here is basically ghosts. You've got an image of the object that's in focus, and then there will be an out of focus, blurry, larger one. We call that a ghost, right? And not all ghosts are in focus, and those that are not are also scattering light across the whole field. And this is reducing the contrast in the image, and that is not very nice for being able to see fine detail. Now, the Barter planetarium eyepiece here at the top left, that's got what they call phantom coatings. And despite the harsh lighting, under normal conditions, you can't even see the glass surface unless it's got dust on it. It's amazing, right? Anyway, all of these measures are improving the contrast in the observed image and therefore improving the quality of your view. Okay, so the next segment is accessories. And this is a shorter segment. And accessories are things that work with the eyepiece, and you consider them to be maybe part of the eyepiece or part of the telescope as you wish, but they're working closely with the eyepiece. So these can be things like a Barlow lens, a telecompressor, field flattener, chroma corrector, or filters. And these typically fit between the telescope and the eyepiece or the camera, right? And some screw in either to the instrument or onto the eyepiece on the front. Others just slip in like eyepieces do into your focuser. And you can argue whether they're part of the telescope, part of the eyepiece, but the point here is to improve the performance of the system as a whole. And of course, along with that, as a double-edged sword, they can also introduce their own issues, which may degrade the image in some way. And we'll look at each of these in turn. So what's a Barlow lens? Also called a tele-extender. This is a negative lens, and its purpose is to achieve a longer instrument effective focal length, or if you prefer, you can call it a shorter eyepiece focal length if you want to consider this to be part of the eyepiece. So, but basically what it does is it accepts the beam of light that would normally come to a focus here, as shown in green, from the telescope, and it spreads it out so that you've got a shallower thing here, a narrower cone of light. And that is much gentler on the eyepiece. These steep cones of light are very harsh, very difficult to deal with. And unless you have high quality eyepieces, you will not get a nice image from a short focal length telescope. So it helps to enlarge the image, because by increasing the apparent focal length of the telescope, you get a larger image scale. So you can use this to boost the magnification for visual work. And they're usually available with a magnification factor of 1.5 to 2, 3, or even up to 5 times, right? The early Barlow lenses were really bad quality, and they produced degraded images, and they deserved their bad reputation. But modern apochromatic Barlows are actually really good, and they use exotic extra low dispersion glass, and they are remarkably inexpensive. So they can help simple long focus eyepieces to get a higher quality, high power image, while retaining the comfortable eye relief that you get with a long focus eyepiece. And particularly to help deal with the broad cone of light that would normally be too harsh for the simpler eyepiece design to deal with. Now, you can take these Barlows and you can stack them one in front of the other, and you will get a very high overall amplification factor out of it. But although this works, the image quality will suffer. And we saw earlier that a lot of modern eyepieces, which have very complex designs, typically have effectively a built-in Barlow element. And so if you put one of them onto your Barlow, you're really stacking the Barlows, and you're probably not going to get optimum results. But if you only have a handful of eyepieces, that is one way to get additional effective focal lengths. And in other words, then different magnifications out of your telescope. So it's an economical way to effectively extend the range of eyepiece focal length in your set. But you've got to choose the parameters wisely to avoid duplication. So what do I mean by that? Here I have, in this column here, the native focal lengths of a range of eyepieces. Now you might start off with, say, a low power eyepiece of 25 millimeters, medium power of 15 and 10, and then a high power of 5. That's quite a reasonable set of eyepieces to start with, right? But if you put on a Barlow, and here I've got 1.4, 2 times, 3 times, and 5 times Barlows, what happens is, if you have a 3 millimeter, the 2 times 1 will go to effectively a 1.5 millimeter, right? But look what happens. If you were to say, well, I'm going to buy 1 eyepiece and 4 Barlows, then I will have 5 effective focal lengths. But look, if your eyepiece is a 5 millimeter, right, then your 7 millimeter will also look like a 5 millimeter. And so will your 10 millimeter. So each of these lines across here, if that's a native focal length of your eyepiece, then this is the effective focal length of your eyepiece as you apply the different Barlows. So you'll find that, in fact, there's a lot of duplication of your focal length like that. So it's not a universal panacea, right? Then, if you look at these gray areas here, as you have extreme amplification factors, then your eyepieces are starting to look like very, very short focal length eyepieces. And generally, you'll get an unsatisfactory image quality from this. All right. So old Barlows, unfortunately, tend to be rather crappy. Modern apochromats are excellent. And it's better to use a decent Barlow on older, simpler, long focal length eyepiece designs. And they can be very useful for lunar and planetary astrophotography. The telecompressor is the opposite of a Barlow. So the purpose of the telecompressor is to achieve a shorter effective focal length from your instrument. So you see, before we had the original focus was short and we ended up with a long effective focal length. We're going exactly the opposite way. Now we've got a telescope with a long focal length, and now it looks like it has a shorter focal length. These normally screw in place onto the telescope because they're much less forgiving. It's really critical to position them in the optical train properly for optimum performance. These are mostly used for astrophotography, but they can be used to produce lower magnifications for visual use. But it's better just to use a proper low power eyepiece. I will give you a little anecdote later about super low power. Next up is field flatteners and chroma correctors. Now, what happens is, if you have here exaggerated by using a simple lens, the lens has a certain focal length, and so what happens is the beam of light being accepted by the lens is brought to a focus, but as you look out to the edges, you'll find that the focal surface is not a plane, but it's really spherical, convex to the objective lens. So ideally, you want the image to be on a flat plane, but often it is not, right? And this is a function of your telescope. And this is much worse with the short F ratio telescopes, fast telescopes. And in this case, a field flattener will get rid of the problem and will improve your useful field of view, because here you've got a good image at the center, and as you go out to the edge of the field of view, it gets out of focus quite quickly. Next up is coma. Now, coma is something that you usually find in short focal length Newtonians. It's a result of the fact that the parabolic primary can't give pinpoint images all over its image surface. So again, at the center, you'll have pinpoint stars, but then as you go towards the edge, you'll get things that look sort of like comets if you were to enlarge it. So what you have is, instead of a pinpoint, it's a bit of a fuzzy blob with a slight flaring to it, right? So again, short focal length telescopes are more prone to this, and so coma corrector is useful to that. Sometimes you will get something which is both a chroma corrector and a field flattener all in one. Right. So then we have filters. Now, filters are a whole topic on their own, and they're most important for specialist applications, say astrophotography or for solar system observation. And because this topic is eyepieces, I'm just going to concentrate on the visual requirements and ignore the photographic side of things. So onto your eyepiece like these. As I said, the eyepiece in its barrel will have internal threads that allow you to do this. And so you screw it onto your eyepiece, then you put your eyepiece in the focuser, and away you go, right? Or it might screw directly onto the back of your telescope, and this is a sort of thing that you usually find for Schmidt-Cassegrains or Max-Sutov-Cassegrains, right? And finally, you might find now this is very awkward because every time you want to change the filter, you've got to take the eyepiece out or unscrew the thing from the telescope and then put the new one on. So instead, you can have a filter drawer or a filter wheel that will allow you to extricate or to switch quickly from one to another. And with none in, the telescope is normal, and you just introduce the appropriate filter as you wish. And so that's very useful, in particular for astrophotography. Not all is free of problems, of course, because what you're doing is you're adding a space between the telescope and the eyepiece, and you may not be able to achieve focus as a result. This is a bigger problem for Newtonians, and it's much easier for Schmidt-Cassegrains, which have got the ability to focus over a wide range of positions at the eyepiece end. Colored filters were much more important on older refracted telescopes, which had low definition and chromatic aberration, but they can still help today with enhancing certain planetary details. Mars, Jupiter, and Saturn in particular can benefit from this. And as you switch out your filters, you will see different features coming into prominence in your image. This variable polarizing filter, people like this for looking at the moon, which is very bright. And what you do is you rotate the one element with respect to the other. So you're getting cross polarization. And so that will then dim the bright lunar image and make it more comfortable. But they tend to be rather fiddly to operate. And in my opinion, I'd rather just add magnification, which will then spread out the image illumination and present you with a more comfortable level of brightness. Generally, cheap filters are really not worth the price. And I don't really recommend the basic screen filters. But if you're going like astrophotography, well, then you will need something. So I suggest you just understand your needs carefully and then buy what you actually need, not just because somebody says, oh, you should have a filter. Some filters can become part of the instrument itself and just stay in position forever. And one such is this Bardo fringe killer. We recently got one for use on a 26-inch refractor, which being 100 years old doesn't have the most wonderful optical design. I mean, it was premium in its era, but today we have better glass and better computation facilities and better manufacturing facilities. So if you've got an apochromat, you don't need a thing like this. But if you have a short focus in particular, achromat, then if you look at the moon, you'll see like a purple sort of haze around the edge of the moon. And you can get rid of that by means of this. So here we have the light coming from the telescope. And then above it, we have, with the filter in place, you'll see that the extreme ends have been cut off. And that purple haze is a combination of the deep blue and the deep red that you will see surrounding your image. And then next, we've got light pollution rejection filters, LPR. And this is quite useful for astrophotography. If you take, say, an even more specialized one like an oxygen 3 filter, then it will have even smaller range of wavelengths that it allows through. And for certain objects, this will enable you to photograph them with a long duration exposure, but you're not going to get the street lights causing as much of a problem. So this is a spectrum of a low pressure sodium light, and you will see that it's got distinct bands that it emits in, and things like the light pollution rejection filter will specifically cut out these worst areas. So if you have LEDs, right, it's much more difficult, because instead of having a line spectrum, it's got a broadband spectrum. And now you've got to make a complicated filter that can handle this. In this case, the blue heavy light, which seems to be common these days, is much, much more difficult to deal with, because you'll see it's got this big spike in the blue part of the spectrum, whereas the warm white ones are more in the center of your range of wavelengths. You get very specialized narrowband filters available nowadays, which are particularly useful for tri-band astrophotography. They're difficult to make, and there's a high rejection rate, and therefore they're very costly. But the point is to block the line spectra of the ambient light and let through the crucial emission bands from certain celestial objects. But with a modern, cheap, broadband LED illumination, this is becoming almost impossible to deal with, right? And from this small sample, you can see the peaks where it's allowing the light through vary quite dramatically from one to another. So various objects will respond better to one than another, and the range is bewildering. So there's no one size fits all, and you will have to choose according to your favorite objects and your viewing conditions. This is going to require quite a lot of research to find the right one for you. If you make the wrong choice, it's quite costly, because these filters are not cheap, and you also waste a lot of your time and energy. All right. Okay. So inside the eye, you've got additional muscles. So you've got muscles which pull on the edge of the lens in order to stretch it out and make it thinner, or relax, which allows it to sort of, through its own internal stress, sort of go fat again, right? So that's how you focus, right? And then you've got the iris, which is this area around your pupil, which also is controlled by muscles, so that it can enlarge the aperture or reduce it in order to deal with the light. So the pupil, which is the hole in the middle of the iris, you can adjust in order to limit or allow more light in. And the lens, you can adjust the shape of in order to adjust your focusing of your eye. Now, the light enters the eye through the cornea, and it's this air to corneal interface where the majority of the refraction takes place that is used to form the image, and the lens inside is just used to adjust the overall focal length in order to bring the image of distant objects or close objects to focus, right? It's accommodating for distance, right? So really you're changing the effective focal length of the system by changing the lens thickness. And this is called accommodation. The quality of the image produced by the outer edge of the lens is much less than that in the center. And so when it's stopped down, you will have less light entering in, but you'll have a higher quality image, all right? Inside the eye, you've got these tissues that make up the structure, but the structure is kept in shape through internal pressure. So between the lens and the cornea, you've got a jelly-like substance, which is called, it's a watery substance called aqueous humor. And then behind the lens, in the major part, you've got a jelly-like substance, which is called vitreous humor. And these fill the cavities and keep the eye inflated. Now, there's an unfortunate thing about the human eye, which is not common to all creatures, and that is that on the inside of the eye, which is the part facing the lens, right, and on top of your nervous, your sensors is the nerves that have to transmit the signals from the sensors, right? So you also have blood vessels on the inner surface. Now this whole area here, which is your photoreceptive area, is then called the retina, of course, right? So unfortunately, these blood vessels and nerves on the inner part of the retina do degrade your vision, but the brain mostly filters out the static information, so those defects are unobtrusive. They're there, but we don't see it because they're always there, and the brain just blanks them out. But under extreme conditions, like using a telescope where you've got this like fine beam of light coming through, then you've got this unnatural challenge, and you're not used to that, and it can actually allow you to see the blood vessels and so on the surface of your retina. Other creatures have quite different eye structures. For example, cats have got a reflective layer behind their retina, so light that passes through the retina gets reflected back, and so the retina has two chances in order to be able to pick up the photons. And so that's partly why cats have better night vision than we have. Crabs have a very interesting arrangement where instead of the retina being here, they basically got a big spherical mirror here, and the retina is on the back of the lens. And this is sort of like a Schmidt camera, right? And insects are a whole different bunch, and they've got compound eyes with essentially a whole cluster of very small individual eyes that act as one. So this is really waveguides. It's like fiber optics.
Sorry, Chris.
Yeah.
My image is static. Are you showing us different pictures of different eyes, or are you just?
No, I'm showing the same thing, but I'll tell you what's happened is that my laser pointer seems to have gone off. So I've been pointing at. Sorry, I don't know why that happened. Yeah, so it's the same picture, but I was just explaining. Okay, so then if we home in on the various parts, the pupil and the iris. So the beam of light that enters the eye is restricted by the pupil diameter. So as the iris contracts and expands, so your pupil will conversely expand and contract, right? And so the iris is controlling the pupil diameter, and the maximum dilation of this is age dependent, right? It varies from person to person, but for a given person, this will be age dependent. The maximum pupil diameter is usually about 7.5 millimeters, right? So this is like a camera where you have an iris that you stop down and increase your depth of field and improve your image quality within limits. But of course, you get then a fainter image because there's less light coming through. And the maximum pupil diameter, as I said, depends on age, but also genetics, your health, and the lighting conditions. So the photoreceptors in the eye will talk to a particular structure that's sort of between the eye and the brain, and it'll go feedback and say, right, this is too bright, we've got to close down the iris, right? Small kids can have up to 9 millimeter diameter, even though for adults it's usually about 7.5 millimeter diameter pupil when you properly dark adapted, but it can be much less in others, right? And the general tendency is that as you age, so the maximum pupil diameter will become less because the materials involved become less elastic, Right. Now, it's very, very useful to know how much your eye can dilate, because if you're wanting to choose the eyepiece, you've got to take into account the exit pupil from the telescope, and that should match. It must be able to fit into your pupil. Otherwise, you're going to lose light. So this is actually much easier to do than you might imagine, right? So as I said, as you get older, the tissues become less flexible, and then the lens can't change shape so easily, and the iris can't dilate as much. And so our ability to accommodate the conditions reduces as we get older. And knowing your pupil characteristics allows you to make choices of your instrumentation. So what you do is you take a rod. It can be round or it can be hexagonal, like an Allen key, in which case you've got basically two diameters you can choose from, right? And you look at a bright star with it. Now, a star is huge. It's much bigger than the Earth, but it's very far away. So what we effectively are getting is parallel light from the star. But because the star is huge, that light covers the whole Earth and beyond, right? So we can be in the north and south hemisphere and look at something at the equator, and we can both see it. But for each of us, we're getting a parallel beam of light that's got to get into our pupil. So if we can put an object that's round in front of the pupil and we can just still see the star, then it means that the pupil is bigger than this object. And that's because the light's coming in parallel. We can say that. If it was from a nearby source, this won't work. So we've got to use a star for this, right? On the other hand, if we put the object in front and we can move it a little bit and we don't even see the star blinking in and out of field of view, then we know that the pupil's totally covered. So that means the object is bigger than what our pupil is, right? And if the diameter is just right for our pupil, then as we move it a little bit left and right, the star will flash in and out of view, right? So it's quite easy with this to measure your pupil diameter. And you can use things like drill bit shafts or Allen keys, anything like that has a known size, and you can measure them with verniers or micrometers, and you'll be able to know very precisely. Okay, so now about the retina. This is where things become quite complicated. Defects in your lens or your cornea can be dealt with. You can get an artificial lens put in. You can get a cornea transplant even, so you can have quite serious destruction of this part of your eye, and it's possible to do something about it. But the retina, that's not the case. If it gets damaged, you will lose it. So things like retinal detachments, or if you have excessive bright light, like you stare at the sun through a telescope, at an eclipse or something, you can easily just burn your retina and you will have permanent damage from that, right? And of course, you can have mechanical insults to the eye that can also cause permanent damage. So you really need to look after your retina as best you can. And this is the sensor on which the eye focuses an image. And through a complex set of photochemical and electrical responses, photons arriving at the retina are translated from photons into an electrical pattern, which the brain can then interpret. And really, the retina is part of your brain. If you look at your nervous system, this is so closely tied in, and the nerves coming from your retina go directly into your brain, which is like right next door. So there are two main kinds of photosensitive cells, rods and cones. Now, they're called this by the way they look under the microscope. Now, these are long and thin, and they're packed into bundles, and we just see the ends of them if we look at the retina. And so you'll see that the cones have got this sort of conical shape to them. So under the microscope, it'll look like little cones. And the rods is more like flat on the end. So it's round with a flat end. So that's really what why they call that, right? The cones are optimized for high light level, high definition color vision. That's photopic vision. And there are 3 distinct types: red, green, and blue. And here's a distribution of cones near the fovea, which is the most highly densely packed area of the receptors in your eye. And you will see that it's predominantly red and green in the middle, and the blue is like left out towards the fringes a little bit, right? And overall, there are about 7 million cones and about 120 million rods in the retina of each eye, right? So these ultra high definition monitors are laughable by comparison, to the sensitivity, the density of pixels here, right? But they are highly concentrated in the fovea, and they become more and more sparse as you go towards the edges of your field of view, right? And so you've got the fovea, which is a Latin word that means pit, and it's to do with the actual shape where there's a little dimple there. And that's embedded that's the ultra high density area with very high resolution. And then outside of that is an area called the macula. And almost all of your vision happens in that area. And the rest is peripheral vision, which, believe it or not, you can't really see very well. Despite there being all these receptors there, it's mostly movement that you'll detect on the fringes, and you've just got this very small area here where you've got high definition vision, and it rapidly degrades as you go outwards, right? So the cones don't function under low light conditions, and bright, colorful objects like the planets can trigger them, and you can then get high resolution views like that. The blue sensitive cones are more concentrated towards the periphery, and they only account for about 2% of the cones in the eye. So you've got red, green, and blue sensitive cones. So in the center, blue and red, and towards the edges of your field of view, the blue ones are a higher proportion, right? And the rods, on the other hand, are optimized for low light monochromatic vision called scotopic vision. There are no rods in the fovea. That means if we want to look at very faint things, the fovea is actually useless. So our best vision is in the fovea, but it's the least good when it comes to low light level, right? So the rods respond well to low light conditions, and they're slightly more blue sensitive than the average response of the cones, right? And a function of them on the periphery is to detect movement in our environment. And what we will do is it will tell the brain there's something happening there, and then we move our eyes and we bring the image onto the good quality portion of our retina, and then we get the high definition view. So, this is fight or flight reflexes rely on this. When you get blindsided, when something suddenly comes in at your periphery, you take note, because they design that way. So each receptor has nerves, and the nerve then attaches to a ganglion. Now, a ganglion is like a little processor, and it will take information from a number of the receptors and combine it together. Now, in the fovea, there's one ganglion per cone, right? And in the periphery, there are about 100 rods per ganglion. And so that's where the movement detection is mostly happening, right? So Perception of faint light and small detail is therefore highly dependent on the number of ganglia involved, because each ganglion will take some group of receptors and it'll combine this information, and then a nerve from that ganglion will go to your brain and let your brain know what is happening. And the brain will then correlate the information, and if it gets information from 20 ganglia that there's something there, then it's going to believe that there's something there. If there's only one ganglion that says that there's something there, well, then it's less important and it'll be ignored, right? It's not brought to your consciousness, right? So the result of this is that you've only got a 40 to 50 degree field of view that is like really good, and that's generally quite sufficient to provide a satisfactory detailed view. We perceive our whole environment to be very detailed, but what's actually happening is we're rolling our eyes around, we're turning our head, and our brain synthesizes a wide field, high definition view from a bunch of snapshots, mostly from the macular area, right? Now, the photoreceptors are extremely sensitive. And in addition, we have a secret weapon in the form of a chemical turbocharger. There's a substance called rhodopsin that is excreted from the eyeball and floods the retina. And this then greatly boosts the photosensitivity of the receptors, right? But rhodopsin itself is also light sensitive. So if you have bright light coming into your eye, it's going to bleach the rhodopsin chemical and render it useless. And so that dampens down our sensitivity. So we've got two mechanisms for restricting our perceived brightness. First is to stop the amount of light coming in by closing down our iris. So we've got a smaller pupil. And the second is by making the photoreceptors less sensitive by the bleaching of the rhodopsin. So working together, the iris and the rhodopsin enables us to operate over a vast range of brightnesses. So when it's bright, the iris stops down and the rhodopsin is bleached. And under very dark circumstances, the iris opens up fully to allow more light in, and the rhodopsin is slowly replenished and turbocharges your retina. So when you're confronted with bright light that bleaches the rhodopsin and stops down the pupil, you've got to wait for the rhodopsin to be refreshed before you can see the faint light again. And this is the dark adaptation problem that astronomers know altogether too well. Now, the structure of the retina is a bit odd, and you look from one species to another, you'll see that different sort of decisions have been made in the construction, right? Having the delicate photoreceptors buried below the nerves and blood vessels makes it easier for the body to maintain and protect them, which is important for long-lived species to retain their good vision. But it has a distinct disadvantage that for the nerves to reach the brain, they have to bundle together and come through the retina in order to get to the brain. And so at this location, there are no photoreceptors. So this is a blind spot. Now, because of the asymmetrical structure of the eye, you'll see, if we take a line from left to right here, you'll see that the fovea is above the center line and the blind spot is below it, right? So because of that asymmetrical structure, and due to the fact that the eyes are mirrored and the brain integrates the information from the two sides, right, we don't normally know that we've got a blind spot, right? Because the brain fills in from the other eye what is blocked on the blind spot. But in astronomy, we commonly use only one eye at a time. So the blind spot can become more apparent and the view through the eyepiece is quite an unnatural thing. And because the fovea is off center, and that's where our peak sensitivity and acuity are. We learn to move our eyes slightly off the target and use a nearby area, right, instead of the center of the center line of the retina there. And that's called averted vision. These are tricks that advanced observers learn. That's not too difficult, but you have to work at it, because what you're going to do is override your unconscious image processing system forcefully with your intellect. All right, so what we've got here is like photographs of the rods and the cones, and you can see at different angular distances from your fovea, their distribution varies. So what we have here, that the cone density is highest, it peaks here in the fovea. And the numbers are absolutely staggering, right? Just how many are packed into that small space, right? So the fovea centralis is only about 0.3 of a millimeter in diameter. There are no rods, just the cones. And the structure is optimized to prevent scattering so that all the light is utilized and there are no blood vessels to obscure it. And on top of that, the eye dithers. It looks left, right, up, down, small movements the whole time to keep the object and to keep the light from the object of interest falling on the fovea, where the bulk of the cones reside. With averted vision, we take into account that the rods, which are better at low light level, actually peak in their density outside of the fovea. Right? It's still within the macula, but outside the fovea, right? And so averted vision takes concentration, but the rods are 1,000 times more sensitive than the cones are to light. So despite their sensitivity to blue, detail in the blue is difficult to see. The blue cones are outside of the fovea, and instead we're using the rods under the low light conditions. So when we naturally focus in the real world on the red-green area, the blue is out of focus. Now, that's not really strange because it's only things like the sky and light reflected off lakes or the sea that is blue. Mostly things around us are green, so it's not really surprising that we should favor the color vision in that area. Now, incidentally, the additional glia in the retina, which are blue sensitive, but they don't actually contribute to vision. These affect the body's diurnal response to ambient light and influence the balance between insulin and glucose. So blue artificial light can have profoundly adverse health effects as a result of these glia being triggered the whole time. So basic specifications of the human eye. So the focal ratio, which we also call the F number, this is not ultra fast, but F2 to F8 is quite a decent range, right? The quarter degree field of highest resolution vision is about the same size as your little fingernail held at arm's length, right? It's about half a degree. So that's the same diameter as the moon. So if we look at the moon and we focus on it, then that is the field of view with the highest acuity. The definition drops off rapidly towards the edge of the field, and the outer edges are really only good for detecting movement. And for this reason, considering that the field of fair definition is 48 degrees, right? You only really need about a 40-degree apparent field of view eyepiece, and going beyond that is a luxury. As I said, what we do is we roll our eyeballs around to see the rest of it. But if you're looking at an object and it's in the center of the field of view, you really don't need ultra-wide field of view eyepieces. Okay. Now, the quantum efficiency of your receptors is boosted when dark adapted due to the chemical supercharging of the rhodopsin. Some photoreceptors can even respond to single photon events. I find that absolutely staggering that we can detect a single photon, right? And then we have neural image processing that plays a part in sorting the signal from the noise. So we've got natural noise rejection going on inside our eye-brain system. So now I'm going to try a little experiment with you, all right? You see this? It says, I bet you can't read this, or even this. Can you? I'm sure you're going to say yes. But if you just stare at this for a while, just look there, focus your attention there, so you don't have to put too much time into it. You look here, while you're looking there, I'm sure you can't see the rest. You can't read it. It's there, but you can't read it. I'm talking about normal distance from the screen or normal projection. Does anyone want to give me feedback on this?
Hi, Chris. I mean, I can still see that there's writing, but
can you read it? I bet you can't. You know, there's something there. If you're looking in the center of this little image here, where I put the red spot, I bet you can't read the text.
But isn't that true wherever you're looking at the screen? Is it particular to the blueness of it, or is it just that?
No, I'm just saying the angular distance from here.
Oh, yes. No,
there,
you can't. You're right. Yeah, I agree.
So there's an area here that you can see with high definition, and you didn't even notice that you couldn't read the rest of this normally because you scan around and the brain integrates everything, right? I'm just illustrating to you that the field of view of acute vision is actually very small, all right? So I think you must bear this in mind to inform you when you're considering really expensive eyepieces, right? Okay, so seeing faint objects in detail. You mustn't expect to see Hubble Space Telescopes like color because the rods can't do that, right? And we don't see anything bright enough to trigger our cones generally, right? Then as we magnify the image of an extended object, what you're doing is you're spreading the same amount of light over a larger area, so it gets dimmer. So to an extent, finer detail can be seen until you've exhausted the capability. And on the fringes of visibility, the brain correlates information from adjacent ganglia and vote on whether there's something actually there or not. So foreground stars are point sources, and they will look the same irrespective of magnification. That is, unless they break down into blobs because of the limits of instrument definition having been reached. Advice, unless you have severe astigmatism, it's better to observe without glasses. But if you have astigmatism, then you can either get a little clip-on piece that your optometrist can make that you can stick on your eyepiece and rotate it until you get the sharp vision, or you can resort to eyepieces with higher eye relief, and then you can wear your glasses. Now, counterintuitively, sometimes it can actually help to pile in a little bit more magnification, which produces a smaller exit pupil. And that uses less of the eye's lens because it's a smaller diameter, but it uses more ganglia because you've got the image spread out more over your retina. And this is a justification for the experienced observer to have a greater selection of eyepieces suited to the objects of interest. So if you're an eyepiece junkie like me, then you can say, well, you know, there's no one size fits all, so I've got to have special eyepieces for special purposes. Right? So in summary here, the 40-degree field of view is adequate. So why move to the extreme wide-angle eyepieces when you have to roll your eyes around to see the field? Well, the answer, of course, is for large untracked telescopes like big Dobsonians. Wider fields allow the object to remain in the field longer before you have to push the telescope around and then wait for the vibrations to die down. But of course, people also do find them more comfortable. And like big screen TVs and performance cars, once you've had it, there's no going back. So just be grateful that we are no longer using these tiny Ramsdens in 0.965-inch barrels, right? Okay, we're on the final leg now, choosing eyepieces. And here I'm going to try and integrate some of the information that we've learned to give you some advice that you should then understand in the light of your newfound knowledge, right? So many tiresome questions, you know. What is your favorite focal length eyepiece? Well, it depends, you know. What do you want to observe? What are the characteristics of your telescope? What are the viewing conditions like? Will you be dark adapted? How good are your eyes, right? And ergonomics and apparent field of view and eye relief are just as important. So you've got to balance your choice. So generally, one's favorite eyepiece would be comfortable, sharp, medium power. And this all revolves around the exit pupil. And we use the focal ratio of your telescope to guide us in our selection of eyepiece focal lengths, as I will explain now. So magnification can be varied by changing the eyepiece focal length. And you should choose it not in terms of the power, but in terms of the exit pupil, because that's a universal constant metric that you can be guided by. So for any given telescope, the magnification is the telescope focal length divided by the eyepiece focal length. It's the same as the apparent field of view divided by the actual field of view, and by the entrance pupil, which is the diameter of your objective, your primary mirror or your objective lens, divided by the exit pupil, which is the diameter of the beam of light that is leaving the eyepiece and entering your eye. So because these are all the same, we can equate one to another, and that provides us with some ways of analyzing what we need. So what we want to do, firstly, is match the eye's pupil. So if the exit pupil is too big, then you have excessively low magnification. And what happens then is insufficient ganglions are involved, right? So that means that the brain doesn't see that the stuff is there, even though the retina is picking it up. Now, there are more issues than what I'm listing here. So the exit pupil, just to, because I've used the term, but I haven't really told you what it is. It's the diameter of the beam of light that is leaving the eyepiece. And in daytime, if you just step back from your telescope and you look at the eyepiece instead of through it, then you'll see it looks like a little bright disk of light that's floating just outside the eye lens of the eyepiece, right? Now, most of the instruments that we have a central obstruction. So, you know, the Newtonian secondary mirror or your Cassegrain secondary mirror. And the shadow of that leaves a hole in the center. So here's your exit pupil, and here's a hole in the middle where the secondary shadow is, all right? So obviously, the diameter of that hole in the middle scales with the diameter of your exit pupil. So as you have a very low magnification, so long focal length eyepiece, so you will get a bigger exit pupil. And then the diameter of that obstruction gets larger and larger. And as this now approaches your pupil of your eye, it'll be very, very annoying. You have to offset your eye to the side in order to be able to see the image, because otherwise it's just blocked. You've just got that sort of dead zone there, right? So this, of course, is worse with fast telescopes, that's short focal ratio telescopes, which have a larger secondary and therefore also a larger secondary obstruction. Now, every part of your cornea that the exit pupil passes through contributes to the image, and the optical quality of your eye is worst around the edges of your lens, right? It's best in the center and it's worst towards the edges. And that means at very low power, when there's a large exit pupil, no eyepiece, no matter how perfect, can show truly pinpoint stars because of the poor outer part of the cornea, bringing that part out of focus. So you've got good image and progressively worse image as you go from the center towards the edges of your pupil, and these are all overlaid on one another. So that means the eyepiece can be fine, but your eye's lens isn't, right? Now, this shouldn't stop you. You just need to be aware of it. Now, remember I mentioned that you have nerves and blood vessels running on the surface of your retina. Now, at high magnification, they start to become evident because then you've got this very small, narrow beam of light coming out of the telescope. And this then can cast shadows of that. If you've got a larger size exit pupil coming into your eye, then that beam covers more of your retina. And so you just can't win, you know. If you go to the extremes, too small or too big, then it just isn't right, you know. So it's a bit like the curate's egg, you know. It's good in parts, or like Alice in Wonderland, you know, getting too big or too small. So now I promised you an anecdote earlier about extremes of the exit pupil, and I used a 0.63 times telecompressor and a 75mm eyepiece on my 10-inch Schmidt-Cassegrain, that's a f10, to achieve extremely low power. This gave a huge exit pupil, so like this, right? And so if I put my eye centrally on it, I could hardly see anything because I've got this big black spot in the middle just covering my pupil. But by offsetting my eye and using just this part of the annulus here, I was able to use the telescope at this extreme low magnification. Of course, all the other light that the telescope had gathered was lost, but I'm still getting the brightest image possible at that magnification, right? And with that, on the 10-inch long focal length instrument, I was able to see Barnard's loop in detail. That was really quite nice. Okay. So still on the subject of this business of the extreme exit pupils, you might recall there was a time when these very illustrious, very experienced observers started drawing pictures of Mars, right? And these had these canals all over it. But, you know, when we spent spacecraft there, we didn't see that, right? And with the telescope, neither did equally esteemed visual observers like E. Barnard. So the question here is, why did they see this, right? And it was there enough for them to be able to make these drawings and say, well, it's always like it. Whenever I look at it, that's what it looks like. And so the most probable thing is that they were superimposing the internal structure of their eye onto the image. So the shadows by these extremely small pencils of light coming out the eyepiece, the shadows of their nerves and their blood vessels on their retina were throwing shadows onto the retina itself. And so there were these dark lines and spots that they were seeing there, right? There is perhaps another component, just to be fair, and that is that a guy called William Hartmann, who was a Mars imaging scientist from the 1960s to the 2000s, explained that the canals could have been streaks of dust caused by wind on the leeward side of mountains and craters. But, you know, I don't think that's altogether the case. All I can say is that back in the 80s, my sketches of Mars looked more like this than they did of that. And at the time, I wondered why mine should be so different. All right, now some recommendations. You will read in the literature, you need so much magnification per inch of aperture. This is just nonsense. Concentrate on the exit pupil size. That's the simplest and most appropriate method of choosing eyepiece that is good for your telescope, right? So to get the eyepiece focal length that will produce the desired exit pupil diameter, you simply multiply the desired exit pupil in millimeters by your focal ratio of your telescope. And that means that, say, that means that for a given focal ratio, right, you can have a whole range of telescopes that can use the same eyepiece set because this is a constant. So, for example, I've got a 4-inch and an 8-inch, and I had a 10-inch and then a 12-inch and now a 14-inch Schmidt-Cassegrain. They're all f10, and all of them can use the same eyepiece set because they're all f10, right? If you have like a f5 refractor, you will have to adjust your set accordingly. But if you have a f5 refractor and a 10-inch f5 Dobsonian, they can use the same eyepiece set. So remember that under light condition, you don't fully dark adapt. And so the maximum pupil dilation will probably not be achieved. And that means your pupil is smaller and you can't have such a wide exit pupil with that extreme low powers would give. So you have to limit your lower power. And on the other side, remember that the hole in the exit pupil can be objectionable at low power, especially on bright objects where your pupil contracts, but the hole in the image is still there. And on the opposite extreme, with high magnification, as I said, you'll highlight defects in both your eye and the instrument, as well as suffer the atmospheric issues to a greater extent. Again, bolos can be useful, but adding a bolo to an already boloed eyepiece is not very satisfactory, and it's better to have a dedicated eyepiece. So this is my recommendation. You go according to your exit pupil in order to determine the range of eyepiece focal lengths that you want. So sometimes you can get a bargain by buying a set of eyepieces in a family. And these Baader Hyperions here are excellent quality, both optically and mechanically. And they're part of a system that allows the eyepieces to be used in unusual ways. And they've got exceptional coatings, right? But the question is, do you need the whole range? Well, probably not, you know. As for the lesser quality kits, well, you know, Celestron's fine. There's nothing wrong with them. And the set on the right here is probably more desirable than a generic one on the left, purely because of quality control issues, right? But so what are you getting with this? You're getting a case, which is nice, and you're getting some filters, which you will probably never use, right? But the biggest question is, do the eyepieces fit your actual needs, right? Are they a good fit for your telescope's F ratio? And will you be able to house all your eyepieces as your collection grows over time? So kits are generally a marketing ploy. They entice you to think you're getting a bargain on the basis of counting all the individual pieces, right? Yeah, you must focus on putting your money where the quality is important, right? So do your research and preferably try before you buy if you possibly can, and just get what you need, right? In time, your set can grow as your needs change or you get opportunities, but be very judicious, especially when you're starting out. So where to start, right? Yeah, only you can prioritize the considerations. Firstly, quality counts. So a good eyepiece can make a poor telescope shine, whereas a bad eyepiece will make a good telescope disappointing, right? There will always be advances in design and materials, but the physics remains the same. So be practical, be careful what you wish for because you might get it, right? And remember that buyer's remorse is very painful. Don't be in a hurry, be discerning in your choices, and consider secondhand. There are bargains to be had. A good eyepiece that's looked after is just as good 50 years later, right? And there's always somebody who's wanting to trade up and others who are wishing to rectify their mistakes. So you can find good quality Barlows on the market. And if you choose, say, 7, 5, 3, and 1 exit pupils, and you add a 2 times Barlow, then effectively you're going to add in there 3.5, 2.5, and a 0.5. You don't really want to go below a 0.5 exit pupil, because, as we said, you will start to see the defects in your eye rather than an image. Get the best you can afford, right? If you buy a Barlow, make sure it's a high quality one, and remember that some eyepiece designs do include built-in Barlows, and so they don't Barlow particularly well. It's really very important to dry your eyepieces. Let them dry. They will attract condensation if you bring them inside and they've been cold outside, because inside the warm air will have absorbed moisture, and now you've got this cold thing and the water will condense out of it. And that can promote fungal growth inside, and that's not good for your eyepieces at all. You really can't recover from that. So if you're faced with the extreme of going from outside where it's cold to inside where it's warm, then put them in a Ziploc bag and let them acclimatize before you take them out of the bag. And this I put in my eyepiece case. It's a little sort of sieve thing with silica gel packets inside. So use desiccants while you're storing them to reduce any possibility of moisture condensing on your eyepieces, right? Treat your eyepieces to a case. I mean, even you know, poor eyepieces are still precious, so look after them. So get the best you can afford. Buy in a considered sequence. I suggest you start with a medium power, then go to a low power, and then a high power, and then finally you can consider extremes or a Barlow, right? Decide on what's important to you and prioritize your needs. Remember that the same eyepiece can behave differently on different telescopes because of the focal ratios mostly, right? So if you through as many combinations as possible and borrow, try before you buy, and experiment with your telescope on the objects you want to look at. And finally, you can do it yourself. You really can build your own eyepieces. These are just examples of things that I've built. This one I gave to the Society for use on the 26-inch. And this is an 8-element. So is this 35mm one. These are 8-element eyepieces. They're made out of junk, but they perform really well. Now, I ask you, do you think that this cheap and nasty made out of a piece of the handle of a pool cleaning equipment for the barrel and so cricket bat grip cover for to give you a nice grip on it, do you think this is the equivalent of a TeleVue Ethos? Well, clearly it isn't, and yet I swapped one of these for one of those. And the reason for that is this was a very bad eyepiece for the needs of the person. 3.7mm, that's a very high-powered eyepiece, and it's very heavy, and this was going on an 18-inch Dobsonian. Scopes would just nosedive if you put this on. So it was miserable to try and use it. This very high magnification that was resulting meant that the slightest vibration was just miserable. Whereas the 35mm eyepiece was what she really needed, right? So we both went away happy with an exchange of a homemade eyepiece versus a very expensive TeleVue eyepiece, right? So it's fun, satisfying, cheap, and effective. Don't rule out. Once the bug bites, you might find yourself making eyepiece after eyepiece. And it's really nice to be able to see people's delight at a good image resulting from cheap stuff. And it's quite edifying. So thank you for your attention. And that's the end of the presentation. If you've got questions, I'll be happy to answer.
Thank you so much, Chris. I really think that was well worth the hour and a half that you requested. I don't know if you used it all up because I was so enjoying your talk. Does anybody have any questions?
Yes, it's you.
Yes, thank you very much for your wonderful talk. And I always impressed by your deep knowledge about astronomy and even the human's body, eyeballs. Let me ask you one question. Imagine you were invited to a large star party. There are a lot of various telescopes, from refractor to catadioptric type telescope, from large to small, but you are allowed to use only one eyepiece. What do you choose, focal length and the type of the eyepiece?
Yeah, that of course is a trick question in a way, because you know that there's no one size fits all, right? You can't optimize for all the variety of possible instruments. However, if you choose a medium power eyepiece, sort of mid-range in the focal length, and with a reasonable field of view, and that it isn't too heavy, and that has good eye relief, and importantly, that it's got good contrasty optics, right? Because quality counts. Then I think you can walk from one telescope to another and enjoy the views. But it also depends what objects those telescopes are pointed at, right? As to what would be the appropriate thing. So it's what are the characteristics of the telescope and what is the object, right? And how well dark adapted are your eyes, right? These all count, but you will find a range going from, say, 5 millimeters up to 40 millimeters. And if you choose around a 20 millimeter eyepiece, that will work on most telescopes and you'll get a view. It might not be optimum for the object or for the telescope, but you'll be able to get a view. And if it was a good quality, decent eyepiece, then at least you've got a means of assessing the telescope's performance versus the eyepiece's performance, because you know the characteristics of your eyepiece.
And let me ask you, would you recommend to use zoom eyepiece for the beginners?
I would say generally not. I'd rather suggest that the beginner gets 3 eyepieces, nothing too extreme, all right? But if you've got a good quality zoom like the Baader, the Hyperion zoom, then that would be okay. But generally, I think you're better off spending your money on a few decent eyepieces than on a zoom for all things. But I understand, you know, as I said, if you've got like a library telescope, something that you lend out to people and you bolt in place so that it can't be removed, one eyepiece, then a zoom is really, really useful. And a zoom's also useful at star parties because you can quickly sort of like zoom out to get the field and find the object again because the telescope is bumped, and then zoom back in again. So it definitely has its place, right? But I wouldn't suggest that you get a zoom only, right?
My answer to my question is I will prefer to choose Nagra type 30 millimeters that has a very wide view, 100 degrees, and that means just same as 2 times of the magnification of general 50 degrees field of view, and that's very useful from the planetary observation to the cloud of galaxy for every object. And I don't recommend the use of the zoom eyepiece because the quality is not changed even if the magnification was changed from to small to large. So that is my answer.
No, I understand what you're saying. Let's face it, it's nice to have a wide field of view, a wide apparent field of view. But as I illustrated, you enjoy this by rolling your eyes around, not just by looking at one part of the image all the time. But if your interest is, say, variable stars or double stars, you don't need a very large field of view to be able to do your work. But what really does count is image quality, right? It has to be very high definition, right? If you're wanting to do lunar and planetary work, you will want to use generally a higher magnification than for nebulae and star clusters, right? And you don't mind that the field of view is a little bit smaller. If you're wanting to just browse around the sky and enjoy nebulae and star clusters, follow the Milky Way and so on, then you would like to have a wider field of view and a lower power, so that together the true field of view is larger, right? But when you come across, say, a cluster that you want to look at, you'll want to zoom in on that, and then you will want a shorter focal length eyepiece to give you more magnification. So there's no one size that fits all. I mean, we know that there's a range of eyepieces that are sort of generally applicable, but if you've got a range of telescopes from, say, a f4 up to a f20, right? Yeah. Then there will be just a few eyepieces that are good on all those telescopes, and the rest you will say, well, this one for that image on that telescope, that's what I'm going to use, right? So it's not a straightforward one size fits all kind of answer that you can give.
Okay. Anyway, thank you very much for your wonderful talk. I enjoyed your presentation tonight.
Thank you. And yes, Nagla is good, but you know, Teleview make other things like the Ethos range as well. They all have their place, and the Nagla was the earlier range. They've got better since then.
Yes, I agree. Thank you.
Okay.